Amazon's Simple Storage Service, or S3, serves as a storage plane designed to manage exabyte-level datasets across trillions of objects. While systems like EBS and EFS handle local and networked workloads, S3 is architected as an independent object-based storage environment. It operates as a cloud-scale key-value repository, treating metadata as first-class citizens, routing data to backups, disaster recovery, and static web distributions. Building secure and performant systems on this infrastructure requires an engineering approach that prioritizes S3's specific API behavior over traditional hierarchical assumptions. This requires navigating regional physical constraints, string-based namespaces, and deterministic Boolean security gates. Understanding these under-the-hood API constraints is necessary to build a resilient, highly available data layer. Although the AWS console presents a unified interface, every bucket is physically anchored to a single AWS region at the moment of creation. This regional selection is permanent, dictating the physical boundaries for data residency compliance and the baseline for network latency. S3 routes requests globally by utilizing a shared global namespace, which connects these regional buckets into a single DNS routing tree. This is distinct from an account regional namespace, where standard resource names are isolated to a specific account or region and can be reused. In S3, the namespace mandates absolute uniqueness across all AWS accounts worldwide. If a bucket name is registered by another user, it is unavailable everywhere. Attempting to create a bucket with an existing name results in a BucketAlreadyExists exception, halting the deployment at the API level. Because S3 buckets resolved as public DNS endpoints, 5 precise character-level naming constraints must be met to ensure successful global routing. First, bucket names must not contain uppercase letters or underscores. Second, the name cannot be formatted as an IP address. Third, every name must begin with a lowercase letter or a number. Fourth, names cannot begin with the prefix xn-, a sequence reserved for internationalized domain names. Fifth, names cannot end. Violating these string constraints triggers an immediate API validation error, which will break automated deployment pipelines. Programmatically, S3 has zero physical concept of directories or folders. It is a flat key value store. While the AWS console uses folder icons to assist human navigation, the system itself only recognizes a single string. That string is the key. It represents the absolute path, which we can split into the prefix segment and the object name. This flat structure supports significant object sizes. This scale shows the maximum limit for a single S3 object at 50 terabytes. S3 does enforce a mandatory upload threshold. Any file exceeding 5 gigabytes must be processed using a multi-part upload. Multi-part upload divides the file into independent parallelized byte streams, which improves transfer speed and protects against network failures. It is a best practice to use this method for any file larger than 100 megabytes to optimize transfer performance. Administrative data is attached directly to the payload. This includes system and user-defined custom metadata, as well as a collection of tags. Each object can hold up to 10 custom Unicode tags, which are used to manage security policies and storage lifecycles. If versioning is active, a unique version ID is stamped onto the object. This identifier allows the system to track every modification to the object over its entire lifecycle. Because S3 operates as a taggable key value store rather than a hierarchical drive, it avoids directory-based search bottlenecks, enabling rapid retrieval of millions of objects. S3 access is governed by a dual-layered security model that coordinates user-based and resource-based policies. User-based security relies on IAM policies to define which API actions a specific user or role can perform. Resource-based security is attached to the bucket or object itself, using bucket policies or object access control lists. The evaluation logic follows a specific Boolean formula. An IAM principal is granted access if their IAM policy contains an allow statement, or the resource-based bucket policy allows it. However, this only holds true if there is no explicit deny statement in any applicable policy. An explicit deny serves as an absolute override. It supersedes any other allow statements, immediately blocking the request. These rules are defined in a JSON bucket policy. The principal block shown here identifies the specific user or account the policy affects. The action block lists the permitted API operations, and the resource block defines the target buckets and keys using Amazon resource names. The condition block allows for dynamic validation, such as ensuring a request originated from a specific VPC endpoint. This deterministic logic gate ensures that security is applied consistently at the raw API level. To prevent data leaks, S3 includes block public access, an overriding circuit breaker that acts as a perimeter defense for your data. This guardrail overrides any individual bucket policies or ACLs that attempt to grant public access. When enabled, the system follows 4 rules: blocking public access from new and existing ACLs, as well as new and existing public bucket policies. Enabling this at the AWS account level creates a global safety perimeter across all current and future buckets. This guardrail ensures that even if a policy is misconfigured, sensitive assets remain shielded from search engine indexers. We have analyzed S3's namespaces, flat keys, and security boundaries. In Part 2, we will apply these foundations to object versioning, delete markers, and replication dynamics.